Okay, ladies and gentlemen, this is a demonstration of area and volume questions in a Calculus 2 setting, and I promised you all I would get to some examples like this, and here we are. So we're going to work with these today, and let's see if I can make this bigger for you guys here. I guess we'll just keep it this way. Alrighty. So let's go over some area and volume questions. And so I'm going to do the odds and leave the evens for you to do. We first want to look at what's called the bounded area with all these curves here. So this first curve is in black. This is an exponential curve. And as you guys can see, you have the exponential function in black here. When they say y equals 0, that's code for the x-axis, and it looks like that's in purple here. So I want to describe that here in terms of the colors. There's your x-axis. When x is 0, that's the y-axis, so that's in blue. Okay, so, and then you have x is 5 now, and then that's in green. So I'm going to kind of just go through it this way for you guys today so you guys can see the colors. So when they're talking about a bounded area, they're referring to this portion here, right? Or the area bounded by all of these curves here. Talking about the boundaries there. Okay, so we're going to try to find the area bounded by these curves. And some of you guys remember from Calculus 1, what I like to do is I always draw my approximating rectangle. And there's my delta x. There's some x value. And so we're going to integrate this here. This is the area. This area is going to be the integral of the curve y dx over that interval here from 0, looks like to 5. Okay, so this is what we have here for this first question in our area and volume demonstration or examples from Calculus 2. All right, now the y value here, or the y variable, is your function. So this is 0 e to the minus 0.4x dx. This is going to be what our area becomes. All right. So as you guys know, this is going to be u substitution, where my u now will be, because we're integrating an exponential function, negative 0.4x du now, or du dx, is negative 0.4. So if you want, I'll use operator notation for this derivative here. And then now, dx becomes du over negative 0.4. So this area here will be the integral of e to the u, dx will be du over negative 0.4. And we're going to kind of think of what happens to these limits here. Okay, because what we can do here now is, remember, if we're going to change these limits, and maybe it's a good idea, you have the lower limit for an x value being 0. So if we let x be 0, we'll see what this u becomes for our lower limit. Negative 0.4 times 0, which will be 0. That's not a mu, that's a u. So u will be 0. This is our new lower limit as we convert our limits as well. And then we're going to convert the upper limit, and the upper limit will be, let's put that in green, that's going to go here. And this happens when u is going to be 5 now. So for the upper limit, we'll get u being negative 0.4 times 5 And that'll be a negative 2, looks like. Okay, so that's a negative 2 here. All right, let's just double check here. Okay. So let's see. Lower limit, upper limit. All right, so my area now will be from 0 to negative 2, e to the u. Let's pull out that constant here. So I'm going to move this out of the way. I'm going to pull out the constant of a negative, that's 1 over a negative 0.4 here, du. So we got my constant there. So this will be negative 0.4 e to the u. Evaluate that from negative 2 and 0. So it's negative 0.4 e to the negative 2 minus a negative 1 over 0.4 e to the 0. Okay, so I get negative 0.4 times 1 over e squared plus 1.04 times 1. So what I can do here now is write this as a negative, that's a 0.4, and negative 0.4 minus 1 over 0.4 times 1 over e squared. We could do it that way. Or simply factor this out. And this is like 4/10. So ladies and gentlemen, if you're looking back at the book, it's like 1 over 4/10. I'll keep this as 1. I'll keep this as 1 minus 1 over e squared. That's like 10/4, which will be 5/2. And I'll just keep it like that. So area will be 5/2, 1 minus 1 over e squared. There you go. There it is. So it's just going to be a straightforward U substitution question here for you guys here. Just area under that bounded region. Okay. All right. Okay, now you're going to have you guys do number 2. I'll work on number 3 here. Another bounded area question. And notice the curve here, y is sine in black. That's the sine curve. Okay, and then in blue is your sine cube curve. X is 0. So that's the y-axis, that's that limit value. And then x here is pi over 2. This is, I guess, we didn't put that curve there, so half a pi, it's right over here. I didn't mark that there, and I should have. If I did, I'd put it in green. So there's kind of a, you know, some of these, this is the bounded region. And then you have the top curve and the bottom curve. Here's what they're looking for again. They really want this area between the two curves here. Okay, that top curve is in black. It's the sine curve. And maybe that's not the best tracing. And then you have the blue curve here. And just kind of pay attention to this kind of detail. Here and here, these points. That's pi over 2. And that's 0 here. All right, so this is kind of what they're giving you. So I'm going to erase all the color so it doesn't distract us. But this is essentially what I see when I see this. Trying to find the bounded area. Now remember here, you have the approximating rectangle. I always draw that approximating rectangle. And there's a top curve and a bottom curve. Remember, this is our delta x, or dx, for some x value. So the bounded area now is going to be for x values that are between 0 and pi over 2. So we're going to integrate from 0 to pi over 2. And if you guys remember, it's the top curve minus the bottom curve, dx. This is where that dx comes from, okay? And this is the height of my approximating rectangle. It's the top curve minus the bottom curve. So you're going to need to know what curve is on top, and what curve is on top is the sine curve. The curve on bottom is actually the sine cube curve. So now my area will be from 0 to pi over 2 sine minus sine cube dx. So this is how we're going to find the area between two curves here. Okay, if you guys remember that from Calculus 1. Now, I'm going to say do some algebra here, or do some trigonometry, right? Algebra, trig. Right in the middle here, we're going to factor out a sine. And you're left with 1 minus sine squared x. And 1 minus sine squared x is actually cosine squared x. So my area will be, if I integrate from 0 to pi over 2, sine cosine squared dx. So what you end up with, ladies and gentlemen, replace this with some algebra, trig, whatever you want to call it. Use your Pythagorean identity here. You end up with a trigonometric integral. And it's a trigonometric integral where cosine is even. So remember, we're going to let u be cosine. And du dx, derivative of cosine is minus sine, which means dx is du over minus sine. Okay? So we have a trigonometric integral. Area is going to be, well, let's see what we can do with this now. So we have sine, and then you have u squared. Now dx will be du over minus sine. Where your sines cancel, you might notice here that I did not put my limits. Okay, now I can do that. Just remember here, though, you have a constant. So you're going to bring out your constant. I didn't apply the limits yet. Now, some math instructors will say, hey, you better put those limits in. Okay, let's put those limits, I guess. If we don't want them to find out that I didn't put the limits yet, sometimes I keep it at the end. You can do that. But let's do what we did prior, right? I'm going to say, here's my lower limit value, here's my upper limit value. This is in terms of the variable x. So if we're going to use u now, u is cosine pi over 2. If u is cosine x, we're going to get that upper limit by doing our substitution with the variable u and applying the value of x. So here's what I'm saying here. We got to get these new lower limit in green, and then new upper limit in orange in terms of u. The upper limit is cosine 90 degrees, and that's 0. The lower limit is cosine of 0, and then that's 1. So u is 0, u is 1. These are our new lower and upper limits. So upper is 0. Oops. Let's find the right colors. Upper is 0, lower is 1. And you know, if I want to, switch the limits and put 0 to 1, then that's a minus the minus. I just have to change the sign of my integral, and that just simply is 0 to 1 u squared du. So now we're fine here. And that'll be 1/2. Sorry, let me stop talking here. 1/3 u cubed from mu is 0 to u is 1, which is 1/3 1 cubed minus 1/3 0 cubed. Final answer is simply 1/3, ladies and gentlemen. There you go. So this is a bounded area question. We found the area to be 1/3, and we had to do a u sub and converted our limits. So this area, ladies and gentlemen, between our two curves is 1/3. Let's get out all the color. We don't even have to label this, but I just want to remark this area is 1/3 between two curves. Okay. That's question number 3. Okay, now let's do question number 5. I'm going to do the odds. And let's see. Question. 4. Okay. Question 5 here is determine the volume of the solid of revolution by rotating the bounded region by the indicated axis. The bounded region. Let's kind of look at what they have with the regions. They gave us curves here. Sine curve again is in black. It looks like it's right here. They give us x is pi over 2. Okay, and I guess that pi over 2 is in blue. It's the vertical line. X is pi in green. It's another vertical line. Y is 0, ladies and gentlemen. I guess I'm going to just use gray. That's code for the x-axis. Okay? So when they're talking about a bounded region, this is the bounded region they're talking about. They gave you all these curves. These curves define what's called a bounded region. And actually, I'm going to take that back. It doesn't include this portion here. Okay? This is your real bounded region because it has all of these regions here. And you're going to rotate this about the x-axis. They said, okay, you're going to rotate this about the x-axis. So here's what I actually do, just like before. If you guys remember, you draw your approximating rectangle. It's a horizontal rectangle, so this will be my delta x for some x value. X value between, let me do everything here. It might be better to say, here's this x value. Pi over 2 less than or equal to x less than or equal to pi. So here's that bounded region here. And notice what you create. So what you want to do is rotate that region, and you should see, and I'm not going to draw a rotated region, but here's my point. Hopefully you guys can see what this creates if you do that. You create what we call a disk. So this is the disk method. Okay. You have the disk method. All right, ladies and gentlemen. So remember your formula for the disk method. I'll include that in a communication to you guys. Area is volume here is just so you guys recall the formula for the disk method. Volume is the cross-sectional area dx from x is pi over 2 to pi for the various values of x. This is our disk. However, your area now, if you guys recall, is represented by pi r squared dx, where r is your y value, or r is the function. Okay, so this is really here. If I try to pick a right color, hopefully you see this is what I'm saying here. This is the radius. And the radius here, this length of the radius here of this disk, from top to bottom, that's the sine curve. Okay, this is what I'm saying. It's your sine curve. So Those of you that remember from Calculus 1, your radius will be sine. Okay? So altogether, here's our area, our volume. It is the cross-sectional area. Pi r, we said, was sine. And of course, we have to square that radius r, and that's dx. So we're using the formula pi r squared. Right here. R is the function is sine. So this is the disk method. Pull out your pi over 2 to pi. This is now sine squared x dx. Okay. Alrighty. Now, I'm just going to say to people, you're going to have to remember a few things here. Okay? You're going to have to remember how to integrate sine squared. And you're going to have to use an appropriate identity for sine squared. So if you guys remember, you're going to use a half angle identity right in here for sine squared. And the half angle identity for sine squared, here you're going to have 1/2, ladies and gentlemen. This is 1. Cosine double that angle here. But remember, for sine squared, it's a difference. For cosine squared, it's a plus. Okay? Anyway, so you get pi integral. Pi over 2 to pi, 1/2, 1 minus cosine 2x dx. Pull out that 1/2. Pi over 2. Sorry, it's a microphone. I don't have my stand with me today, so it's commando style. All right. The microphone just kind of fell on my desk. Let's pull out that 1/2. 1 minus cosine. I got him. I'm setting it up right now where it microphone, geez. Anyway, who needs a mic stand? All right, double check. Hopefully I'm okay. I haven't made any mistakes on this, ladies and gentlemen. Let's integrate x, and this one's going to be a u sub. Remember this one? So I'm going to integrate for u sub. That's going to be 1/2 sine 2x. Let's remember this. That'll be from pi over 2 to pi. Okay? But let's remember the derivative of, do we change the sign? Derivative of sine is cosine, so we're going to keep that as a minus. So I guess we don't change the sign. Let's apply the limits now, right? This is going to be f of pi minus f of pi over 2. Pi minus 1/2 sine 2 pi, and that'll be a minus pi over 2. Pi over 2 minus 1/2 sine 2 pi. So we're doing the upper limit, right in here, minus that lower limit right in here. And of course, there's a difference always. Okay, very colorful. Let's do some arithmetic. All right, well, before I do my arithmetic, here's what I'm going to do. I know what sine 2 pi is, ladies and gentlemen. That's 0, so this is 0. So that's not even there. So now my arithmetic's going to be a lot easier. That'll be pi squared over 2 minus, I think I made a mistake. You guys can see it. I made a mistake. Right in here. This should be pi over 2. So let me double check here. And that makes that sine pi. And sine of pi, does that make a difference? I think that's still 0, even though I made a mistake. But let's go back and double check everything here. Okay? Anyway. Yeah, sine, this will be 2 pi. This is going to cancel. So you really have sine of pi, and that's also 0. So, alrighty. Now let's really look at the details. Minus pi squared over 4. So I can really do my arithmetic now of subtracting 2 fractions by having the same denominator. 2 pi squared over 4 minus pi squared over 4. That's a pi squared over 4, ladies and gentlemen. Here you go. And there it is. So just want to double check my work. And this again is a volume by the disk method, ladies and gentlemen. Your disk method from Calculus 1. Lots of colors. I want to get rid of it. You know, whatever. Anyway. Take that bounded region. Approximating rectangle creates a disk. Disk method. You got it. Always draw that approximating rectangle. It kind of tells you what to do. That's the advice I give my Calculus 1 students. And now we're at number 7. Very interesting question for number 7, ladies and gentlemen. Let's see if we can figure out what's going on here. There's going to be a bounded region again, and they're going to give you the cosine curve. So here's my cosine. Okay, now y equals 0. That's code for the x-axis. So we're going to put the x-axis. That's purple here. And then x equals 0, that's the y-axis. So I guess that's blue. Yeah. And then green, x is pi over 2 here. So when they talk about a bounded region again, this is that bounded region. Okay? And so I always draw this approximating rectangle for my bounded region. Delta x, that means it's going to be a dx for some variable x. And that x is going to be between, ladies and gentlemen, 0 and pi over 2. So we're going to take that bounded region between 0 and pi over 2 for x. We're going to rotate this. But they tell us to rotate now about the line y is -1 down here. So this is y equals -1. This is the axis of rotation here. So I'm going to take that bounded region and I'm going to rotate that. Now, what you guys should see, since you know my art skills are very bad, I want to imagine what I'm looking at. If I rotate that bounded region, if I rotate this, you know, approximating rectangle now, I'll put it in red, about the line y is -1, there's going to be another approximating rectangle down here. So this creates what we call a washer. Okay, because you'll have another approximating rectangle. Let me demonstrate some awful art skills. Point being, you know, you get this washer, something like that. Anyway, right? Yeah. So if you get the washer, let's go back and get this ugly stuff out of the way. What's the formula for the volume by the washer method? Okay. Remember, x is going to vary from 0 to pi over 2. So remember the area for the washer method formula. It's really going to be pi again, r squared. I'll call it top. Sometimes I call that outer. R squared bottom. Sometimes they call that one, and I'm going to clear this out, inner. And my approximating rectangle again is dx. So this is going to be a dx here. Okay, this is the washer method. I want to put that down here. Everybody remember that by the washer method. Now, this is going to be some good stuff because all I need to know is the radius here for the top curve. That's called the outer. So let me remind people here something extremely important to do. I think I'll use purple. The radius, the top radius, is going to be the distance from this point here all the way down here. That distance. And that has a y coordinate. So y top is the cosine curve. Y bottom here is going to be the value -1 here. So if I had to measure this distance, this is what I'm saying to you guys. If I had to measure vertical distance, it's always top minus bottom. Okay? So we're trying to find this radius value, top minus bottom. So it's cosine minus a -1. So this portion becomes cosine x minus a -1, and then that's going to be squared here. All right, I'm not going to put the square there because I'm just finding that radius, and it's for the top curve. But how we measure distance vertically is top minus bottom. So you're going to see here cosine +1. I'll write it there. And don't forget, we're going to have to square that because you have that power 2 now, right? That's what I'm talking about. Now, our bottom. You say, okay, that's great, but what about the bottom curve now? So let me get rid of this stuff, if I can. So here's my eraser. Okay. All right, now you might say, well, what's on the bottom here? How do we do the bottom? I'm going to change the colors now. Maybe we should get pink. I don't know if that's going to help. This is the bottom curve for that washer, right? So this is going to be this distance up here, by the way, is y is 0. And this is still, and that's the y top. This is going to be, I'm going to change the color, but it's still -1. So y bottom is -1. I'm trying to find, again, this distance. 0 minus a -1. So 0 minus a -1 is just the number 1. So when you get this radius now here, maybe purple, I guess. I don't know. Yeah. This radius will be 1. So you say -1 squared. Let's make it purple. Pink. Minus that 1 squared. That minus sign is already here. Okay. And that's because you're using the washer method. So you're just measuring 2 vertical distances. Always remember vertical distance is the top value minus the bottom value. People very much forget how to measure vertical distance. So this is now cosine x plus 1. We're going to square that. -1 squared dx. All right, here's our integral. Anyway, okay. 0 pi/2. We're going to have to do some algebra here. Cosine plus 1 squared by FOIL should be, let's think about that. Is that cosine squared plus 2 cosine x plus 1, and then you have that -1 squared to be -1. So, ladies and gentlemen, I'm going to pull out my pi, and 0 pi/2, you'll have cosine squared x plus 2 cosine x dx. Okay? All right, 2 cosine x plus cosine squared x. All right, now it looks like we're going to have 2 integrals now. Well, let's actually replace this cosine. Let's find out. Remember, we're going to have to replace cosine squared. Cosine squared, I'm going to use purple. Again, half angle. 1/2 1 cosine 2x. But cosine squared is plus, going to be a plus. Right in there. And I'm going to keep the pi out here. Here's my integral, 0 to pi over 2. I'm going to distribute 1/2 plus 1/2 cosine 2x plus 2 cosine of x, ladies and gentlemen. Let's get this over here. Dx. Pi. Now, what I'm going to say here's you're going to use u sub to integrate. Okay, so it looks like we're good. Now let's integrate here. This will be 1/2 x, and this is going to be 1/4 sine 2x. Let's think, derivative of sine, so it's going to not change that sign. Derivative of sine is cosine, so that's going to be plus 2 sine x. And if you guys are in the room, I would ask you guys to check my work. Okay, now we're going to evaluate this antiderivative. F of pi over 2 minus f of 0 here. All right. 1/2 times pi over 2. 1/4 sine 2 times pi over 2 plus 2 sine pi over 2 minus pi 1/2 times 0. 1/4 sine 2 times 0 plus 2 sine of 0. Now here's what this gives you, ladies and gentlemen. This is a 0 here. This is 0. 0. Sine of 90 degrees. Now look at, let's go with this. Sine, this is 2. Sine of pi is 0. And then sine of 90 degrees, I believe this is 1. Okay? So you're going to end up with pi over 4 plus 2 minus 0. And actually, we made a mistake. Let me go back here. It's not what we end up with. Let's try it again. Pi squared over 4, ladies and gentlemen. Looks like it's 2 times 1 there, and then all of this here is 0. So pi squared over 4 plus 2. And I think, yeah, let me double check here. I apologize. We forgot the parentheses here. So this would be 2 pi, actually. Yes, here's my volume. Now we're good, ladies and gentlemen, because remember, we're going to distribute here and way over here. Yeah, pi squared times, or pi over 2 times 2 will leave you just pi. Should be plus pi. Let me double check. Let me double check. Nope. Pi 1/2. All right, that pi was there. Here's where we made a mistake. This is going to be times 1/2. Okay, I'm going to put this, forgot this 1/2 here. Let me go back. Clarify that here. There's 1/2, and this is times pi over 2. Okay. Anyway, let's just double check. So that'll be pi squared over 4 plus 2 pi. Yeah, there we go. Okay, because we're still distributing this factor here of pi. Let's write it very nicely. Let's color coordinate this. Let's get this pi gets multiplied by that 2 over here, right? This is where all the arithmetic I'm saying to focus on and distributing. pi squared over 4 plus 2 pi. There we go. Anyway. All right. Leave number 8 for you guys. I'm going to try number 9 now. Now, notice number 9 here. Determine the volume by cylindrical shells for the, for rotating the bounded region about the indicated axis. So let's see what the bounded region is here. Again, you got the curve. There it is. Y is 0. That's the x-axis, so that's going to be in purple. Okay, and I think this is going to be from 0 to 1. So here's what they kind of gave you. X is 0, X is 1 up here. Let me kind of remark about that. So I guess they have the blue here. X is 0, and then in green here. X is 1. And of course, they're going to rotate about the y-axis here. Okay, so remember, you got a bounded region defined by these curves. If you guys remember that. And interestingly enough, when you create your approximating rectangle, here's that approximating rectangle again. Here's dx. X varies from 0 to 1. And this is my x variable from 0 to 1. Okay, if you guys remember, those are the curves. And now when you actually rotate this, this is not a disc. This is called a cylindrical shell. So this is why they say use that method of cylindrical shells, ladies and gentlemen. You got to remember the formula. V is the integral of 2 pi r h dx. We need a radius of the cylindrical shell that you create here by rotating that. Something like that. You guys remember this? Cylindrical shell, you need a radius for that. And you need a height of that cylindrical shell. Okay? So it's kind of like this. Here's my radius. And then here's the height here. From top to bottom, that's my h. Now the height is the curve. Cosine. It's the top minus the bottom. So let me pick this y top minus y bottom business. So the height is your cosine pi x over 2 minus that 0. In other words, your height, ladies and gentlemen, is just the cosine pi x over 2 function. Now, let me kind of write it nicer down here, I guess. Okay. So my height was the cosine curve, pi over 2x. And then the radius, if you guys remember here, this distance here, the radius is just your x. So r here in this equation here is x, and we have h being cosine pi over 2x, so that the volume function here, the volume equation, the volume goes from 0 to 1, 2 pi r, well that's x, h is cosine pi over 2x dx. So this is your cylindrical shell method. You want to remember that formula here for cylindrical shells and how to get your radius and how to get your height. That's from Calculus 1. So this is kind of reviewing these concepts from Calculus 1. All right. Radius is x, height is cosine. So when I look at this question here, pull out the 2 pi, 0 to 1, x, cosine pi over 2x dx. You might say, what do we use to integrate? Use integration by parts, IBP, ibuprofen. You guys remember that? Integration by parts. All right, I'll do it in purple. Let u be x, du is dx. V is the integral of, or we should do it this way, dv is cosine pi over 2x, and that's really dv dx, or dv, right? We'll put that as dx, so that v becomes the integral of cosine pi over 2x dx. So now you're in the position here when you're using integration by parts, use a t substitution, u substitution. You guys remember it's a different u. I don't know. I mean, maybe you use it. I'm just going to call this a u sub. It's a different u, or you call it t sub. Pick your poison. Okay, now du dx is pi over 2. Simply saying dx will be 2 du over pi. So I need, here's my u, dx is 2 du. So all of this work is to find v. So my v is going to be cosine of u, 2 du over pi, which is 2 over pi integral cosine u. Derivative of sine is cosine, so this would be sine u. Okay, and we know what this u is going to be. This is sine pi over 2x. All right, we need this information for integration by parts now. And you say, what is that going to be? Because the integral is equal to uv minus integral v du. So u is x, v, this would be 2x pi sine pi over 2x minus the integral of v, 2 pi sine pi over 2x. We need du. Du is simply dx. So, okay. 2x pi sine pi over 2x minus 2 pi integrate sine pi over 2x dx. So again, now we have to do a nice u sub. So we're going to have to integrate here. Let's get a u sub. Pi over 2x du dx pi over 2 dx 2 du over pi, I guess. Okay, integrate sine u 2 du over pi. Bring out your constants. Just integrate sine u. Derivative of cosine is minus sine. So this is minus 2 pi cosine u, or minus 2 pi cosine what was u? Pi over 2x. All right, now let's put this together. Don't forget what we had. We had all of this, so I'm going to copy it. I'm going to bring this down. X over pi sine pi over 2x minus, makes that a plus, minus a minus, 4 over pi squared cosine pi pi over 2x. We have to evaluate this from, let's look at the limits now. 0 to 1. All right. This will be f of 1 minus f of 0. All right. 2 over pi times 1 sine pi over 2 times 1 plus 4 over pi squared cosine pi over 2 times 1 minus 2 times 0 over pi sine pi over 2 times 0 plus 4 over pi squared cosine pi over 2 times 0 here. So let's be very careful. Okay, sine of 90 degrees. I believe that's 1. Sine of 0 is 0. I'm thinking of sine curves. Cosine of 90 degrees is 0. Yeah, and cosine is 0. This is 1. So here's what it looks like we have here. 2 over pi. This whole thing is going to be 0. Minus 4 over pi squared. Let me double check here. 2 over pi. Cosine of 90 degrees. That's 0. 2 times 0. Let's double check. Okay. Okay, well. Multiply the bottom by pi here. 2 pi over pi squared minus 4 over pi squared. 2 pi minus 4, everything over pi squared. 2 pi minus 2 over pi squared, I guess. Anyway. Double check the work, ladies and gentlemen. I think we're okay. Did we do that factor minus 2 over pi plus 4 pi squared? We did. Anyway, double check the work. I think we're okay. Integration by parts, ladies and gentlemen. Double check that work. Alrighty. Looks like we went all the way to the next question just to do the scratch work. All right. Okay, let's look at number 11. You got the exponential curve now in blue. Y equals 0. Well, that's the x-axis. Looks like that's in purple. X is negative 1 is in green. Sorry, X is 0 is in blue. Is that in blue? I guess a dark blue, I guess, something. I don't know what color that is. Dark blue? Maybe that blue. And let me double check. Green, well, that's the y-axis, by the way. Anyway. So what they're saying is the bounded curve they're talking about looks like it's right in here. The bounded region, so you guys can see that there. Okay? All right, let's double check. Okay. Now, let's try to do this here. We have an approximating rectangle dx there for values of x between -1 and 0. And then you're going to rotate about x is 1 here, ladies and gentlemen. So you're going to create another approximating rectangle here. All right. And again, you're going to get a cylindrical shell. So, for the cylindrical shell, volume equals the integral of 2 pi r h. Again, this will be dx. Okay, and we need, again, the height and the radius. So my radius value here, trying to find a color here. Maybe we'll stick with the pink, right? This is what I'm saying for the radius value, if you can see it here. Just do it this way. It's this x value all the way to this line. This line is x is 1. So if you're going to find your radius now, it's always going to be a right value minus the left value. This is how we look at horizontal distance. So it's 1 minus that x value. Okay, so we're looking at this radius of this. See if we can find it. From this point to this, radius is 1 minus x. The height now, if I change the colors here, the height of this approximating rectangle is the top curve minus the bottom curve. So my height, the top curve is e minus x, the bottom curve is 0. So the height is just simply e minus x. So I need these two values here. The radius goes right in here. And the height goes right in here. Okay, so it'll be a 1 minus that x value. So, okay. Volume, and that's from -1 to 0. 2 pi 1 minus x. And then don't forget the height of that cylindrical shell, e to the minus x. All right. Okay, now I'm going to say again, so take a look at all this detail. This is my height. Top curve minus the bottom curve. All right, now I'm going to say use IBP. Integration by parts. This is my u. Okay, then dv will be e to the minus x dx. So du dx is -1, or we can say du would be minus dx. V is the integral e to the minus x dx, which really means minus e to the minus x. So by ibuprofen, uv minus integral v du, we get 1 minus x minus e to the minus x minus the integral of v minus e to the minus x du is minus dx. So we get minus e to the minus x, 1 minus x plus, really going to be minus. You got 3 minus signs there. Minus integral e to the minus x dx. And then this integral right in here, minus e to the minus x. Okay. minus e to the minus x. 1 minus x plus e to the minus x. And we're going to evaluate that again from negative 1 to 0. Okay, which is going to be f of 0 minus f of negative 1. So minus e to the minus 0, 1 minus 0, plus e to the minus 0, minus, now plug in negative 1, minus e to the negative negative 1, 1 minus negative 1, plus e to the minus negative 1, I guess. 0. Sorry, not 0. This is going to be a negative 1 here. So this portion's negative 1. This is negative 1. This will be e to the 1, right? This is also e to the 1. Maybe I'll put just e here. Let's see what we got. Let me be careful. E to the minus 0 is 1, so this will be negative 1 times 1 plus e to the 0. E to the 0 is going to be 1. Okay? On top. Minus negative e times 2 plus, it just looks like going to be just e. So let me double check. Negative 1 plus 1, that's going to be 0 here. So we're going to say this would be negative 2e plus e. Oh, that's going to be, sorry. Negative 2e plus e is negative e. And then minus the minus makes that a plus. So it looks like it's just e. So your volume here is e, looks like. Double check the arithmetic. 1, that's negative 1. Okay, I think I'm good. Anyway, double check your arithmetic, ladies and gentlemen. It looks like the volume is just simply an e. So I'll double check these myself, but ladies and gentlemen, I thought I'd get this out to you guys this weekend. I hope you enjoy. Those are some examples of finding area and volume, and take care. I'll see you guys on Monday. All right, so for number 9, ladies and gentlemen, let's go back a little bit and never forget we have a multiple of 2 pi for number 9. So all of that integration by IBP at the very end, we have to multiply this portion. Let's go back again and see what we had here. Okay, I'm going to go back and edit this. And remember that 2 pi. 2 pi times 2 over pi minus 4 over pi squared, ladies and gentlemen. So we get 4 pi over pi minus 8 pi over pi squared. Now that reduces to 4 minus 8 over pi. So here is your volume answer. So here's the volume for number 9, ladies and gentlemen. That's your answer there. Number 11, also don't forget you got a multiple of, this is for number 11, that 2 pi there. We had a 2 pi. So when we did IBP, we're going to put back in that multiple here of 2 pi. So don't forget, this is 2 pi. So that your final answer would be, for volume, for number 11, 2 pi e. We forgot that multiple, but if I find the error, it's not an error, it's not a mistake. This is correct now. All right, ladies and gentlemen. 2 pi e for number 11 and number 9, 4 minus 8 over pi. There we go.